Okay, it's
Recording in progress.
Okay. So far, we've only talked about OLS conceptually, okay? Conceptually. What is the purpose of OLS? Minimize squared residuals, okay? This is conceptually. And then we can get beta hat. But how does the computer actually calculate the numbers? Today we open the black box, okay? Basically, any model is a black box. Inputs, some inputs in, okay, some X in, you're gonna get the output. So this is the black box. So today we're gonna open the black box and do it by hand. So please get your notebook and calculator ready. You can use your phone, right? With matrix. The good news is that there's only one formula, which is beta. Okay, so here I use tilde. Okay, so let's go back to beta hat. So beta hat, this is the only one formula, okay? Equal X transpose X inverse X transpose Y. So this is the one formula for everything in this course, no matter how many X you have. So every regression you will run 1x, 10x with or without an intercept. It's just the same formula. You plug in different x and y. Today we'll see 3 versions of it, from simplest to slightly more complex, using the same small data set each time. Let's take a look at the first example. Example 1.1. So in this case, the model is no intercept, okay? If no intercept, it shows you y equal beta 1x plus mu. Where is the intercept? Beta 0, right? So here we don't have beta 0, okay? Which means no intercept. Okay, so with no intercept, x is just a single column of numbers, okay? Not a matrix, just a vector. That means X transpose X isn't a matrix anymore. And we can also write the formula into this way. This is for summation, okay? This is in matrix. This is for summation. As usual, beta hat, okay? Beta 1 hat equal X transpose X, okay? In the denominator, and the numerator is X transpose Y. Because if you see X power negative, it equals 1 over x, right? Okay, from your mathematics class. So here, the numerator just the summation of xiyi over the summation of xi squared. Okay, so here we have x and y. Suppose these are our data points. Okay, these are our data points. So here, first we need X transpose. Transpose means basically y, X is a vector, right? Like this. If we want X transpose, so the column gonna transpose to the row, okay? Clear about X transpose, okay? So this is our X, and then I have the X transpose in a column. in a row. And y is in column. Okay, so next one. Let's do it step by step. So first, you should calculate x transpose x. So because our data, they are numbers. So basically, x transpose x also means the summation of xi squared, okay? So for each number, just 0 squared plus 2 squared plus all the way through to 5 squared. And you get 137. This one is easy, right? So the first one, x transpose x, is done. What is the next step if you get x transpose x? X transpose x inverse, right? Here means inverse. Inverse just means we flip it, okay? We take its reciprocal. Reciprocal, what is reciprocal? I only know it in Chinese, 导数, okay? You take the 导数, the reciprocal. So you got 1 over 137. And then you got 0.072 around that. So next step, we got x transpose x inverse. Next one, what is x transpose y? Because basically, we get x transpose x inverse, right? The first step. And then for the numerator, you need to get x transpose y. This is x transpose, okay? So you times y, what will you have? It's basically easy just by summation, xi times 1, and you sum it up. So here, 0 times 0 plus 4 times 2, right? All the way through. This is from your linear algebra. And then this is our x transpose y, right? So which is 274. The last step, you just get beta 1 hat. Okay, so here is x transpose x inverse times x transpose y. Okay, so you got 2. This is our answer, which is 2. Okay, so which means beta 1 here is 2, right? So we plug in to our model y equal to x plus mu. The interpretation is if x increases by 1 unit, y increases by 2 units, right? Because we don't have any log transformation here. So those are unit change. In this case, we know that a linear regression equation shouldn't exist. So we approximate it. The approximation is our estimation, which is 2. All right. Next one. Suppose we have our wrong model. So we're omitting beta 0. So y1 equal beta 1x plus mu, but the true model is with the intercept, y1 equal beta 0 plus beta 1x plus mu. Same formula, but now y1 equal those numbers. Okay. The true model has the intercept, which is beta 0 equal 1, beta 1 equal 2. But we forgot to include the beta 0, all right? So because we have the same x, so x transpose x is the same. And also so does to x transpose x inverse, okay? This is x transpose x inverse. But for x transpose y1 is 3 over 305. You can calculate by yourself, okay, later. So here is our new beta 1 hat. In this case, we got 2.22, 627. What is the lesson? Remember, our true beta 1 is 2, right? Our true beta 1 is 2, not 2.22. Why is wrong? Do you know why is wrong here? The true beta 1 equal 2. Compare with our estimate. They are not equal. Why is wrong? Because we omitted the intercept, right? We forgot the beta 0. That's why we got our biased estimator. And remember, whatever we don't put in the model doesn't disappear. It goes straight into the error term, okay? Since the intercept is essentially always there for every observation, forcing it into mu contaminates our slope estimate. This is omitted variable bias, okay? As I mentioned before, showing up as an actual wrong number here. Not just an abstract or formula. We can literally see the damage, okay? The true answer is 2, but our biased estimator is 2.22. Okay, so in this case, beta 1 hat equal biased because it doesn't equal to the true number. Next one. Example 1.3. So in this case, our correct model is y1 equal beta 0 plus beta 1x plus mu with intercept and slope. Okay, so these are our data points. Now we add the intercept. So x becomes a matrix with a column of 1 plus the x value. So basically this column is the coefficient of beta 0, right? Beta 0. And these are the coefficient of beta 1. That's why now our x becomes a matrix. Okay, our x becomes a matrix. This is our x, right? Next one, we need to get x transpose, okay? So the column transpose to row, let me show you, okay? So here is the x transpose. And then as usual, you get x transpose. Next one, you calculate x transpose x. This is the answer. Okay, and then you get the inverse. I'll show you the detail later, but here I just give you the general idea. Okay, you get x transpose x first. It's a 2 by 2 matrix. And then you get the inverse. Be careful about the inverse here. It's not simply 1 over each elements, okay? We have a formula, we call it determinant. I'll show you later. The last step, okay, beta hat. So x transpose x inverse times x transpose y. So 2 by 2 matrix times 1 by 2 vector, all right? So here, how you get 1? You use the row, the first row, and times the column, right? Okay. I hope I can remind you about the linear algebra. And then our estimate, okay? Beta 1 equal, beta 0 hat equal 1, beta 1 hat equal 2. Exactly correct. That means including beta 0 fixed the bias. Of course, you're gonna have the homework, all right? So basically here I showed you 3 examples, right? But one formula, beta hat equal x transpose x, inverse x transpose y. What changed each time was just what we put inside x. 1 column or 2 columns with 1 column added. Everything else follows automatically. So the takeaway for today is that never skip the intercept unless you have a very specific reason to. As we just saw with the real numbers, skipping it doesn't just look messy in theory, it directly biases your slope estimator, okay? Like I showed you here. For homework, assignment 3 asks you to redo this kind of calculation with a new data set. I want you to practice building x transpose x first and x transpose y by hand at least once. Even though when we do the programming, R will do it for you afterward, but you should understand this by hand is what makes the R output makes sense later. I'm done for my part. I think you may have question about here. Do you have any question about here? Yes, you do, but I'm gonna send you the detailed solution. And same as before, discuss with your group. Remember last time we had a group, different nationality, okay? I'm gonna stop the recording here and